All right, so in this lesson, our goal is to be able to determine the infinite limits from the left and from the right sides for functions when you're approaching, a value, x equals c. And we want to be able to, then sketch, a reasonable depiction of what these functions can look like. So we're going to basically be working a lot with one-sided limits, and we're going to be looking at asymptotes of graphs, which you probably covered somewhat in, in pre-calculus. Okay, so let's start off by considering this function where f of x is equal to 3 over x minus 2. Now, we could always graph a function by plugging in numbers, over and over, and, until you get a graph that, or a set of points that looks reasonable to, say, hey, this is what the graph is going to do at this point. But let's be a little more strategic, and let's see what happens to this graph when you're approaching 2. Because, if you plug just 2 directly into x, you would have 3 over 0, so you have an undefined value. So if we plugged in 1.5, you would have 3 over 1.5 minus 2, or 3 over negative 0.5, or more, yeah, which would then give you negative 6. We plugged in 1.9 for x, a value, we're getting closer to 2, we would get negative 30. We plugged in 1.99, we would get negative 300. 1.9999, we would get negative 3,000. So numbers are getting larger in the negative direction. Now what happens if we approach, 2 from the positive numbers? So if we plug in 2.5, you would have 3 over 2.5 minus 2, 3 over 0.5. You would have positive 6 in this case. If we put 2.1 into there, we would then end up with 30. If we plug in 2.01 for x, we'd get 300. And 2.001 for x, you would find that it would be 3,000. So you're getting infinitely large. So in this side, you're getting very, large negative numbers in that sense, and in this side, you're getting very large positive numbers. So it's like, well, then what's going on at 2? It doesn't seem to be approaching any number. You seem to be going in opposite directions. So if we were to graph this function, you would see that the function has an asymptote with the equation x equals 2 as a vertical asymptote, to be very specific, or to be more specific. So remember what a vertical asymptote is, just a vertical line. In this case, x equals 2. And on one side of the vertical line, the function gets infinitely small. It approaches it, but goes, in a negative direction, so to speak. It goes, something like this. So f of x, but goes, trends downward like that. But on this side, when we're approaching it, it's going infinitely large. The function is getting infinitely large. So what we say is that the limit from the negative side of f of x as x approaches 2, so the limit of f of x as x approaches 2 from the negative side is, gonna be negative infinity, because it's going downward, and we call that behavior negative infinity. And when we're approaching this graph from the positive side, we're talking about the limit as x approaches 2 from the right, from the right side. So the one side of the limit of f of x as x approaches 2 from the positive side, instead of it being negative infinity, it would be positive infinity. Usually you can just write infinity without a sign. I tend to like writing the positive symbol because it reinforces, my answer, but you don't have to. And so, again, I like to also, mark, hey, up here we're going to positive infinity, and in this direction we're going towards negative infinity. So this is what we're dealing with when we're talking about infinite limits. And let's now recall that the formal definition of a vertical asymptote. It's going to be essentially, a line where the function approaches infinity or negative infinity as the graph of the function gets infinitely close to it. So in general, we'll say that the asymptote has an equation x equals c. So let's look at a couple different functions, and let's be sure that we can properly write the one-sided limits based on what each of these is showing. So we're talking about, for each of these we have asymptotes x equals a. So let me highlight them just so it's clear with what we're dealing with. So x equals a, x equals a. And they're all doing something different. Something maybe similar but different. So let's look at what's going on with the first graph. Here we have our function approaching from the left side. And what's going on is we're approaching from the left side, the graph gets infinitely large. So we say the limit as x approaches a from the left side or from the negative side of f of x is equal to positive infinity. Okay, you don't have to write that. You don't have to write that positive sign, but I like doing it for whatever reason. Now in this graph, we have the function coming from the right side, so from the positive side, and it's also going towards positive infinity because it's going upward. So we're going, again from the positive direction. So we can then say the limit as x approaches a from the positive side, from the right side of f of x, that's also going to be positive infinity. Now in a third graph, we're coming from the left side, or the negative side in this case. We're going along this path here, and we're going downward. We're going towards negative infinity because we're getting smaller and smaller. So we're going lower and lower. So we see the limit as x approaches a from the negative side of f of x is going to be negative infinity in this case. And for this last graph, we're coming from the positive side, but we're getting infinitely negative or infinitely, downward we're going. So again, we have the one-sided limit from the positive side of f of x as x approaches a from the negative side, or from the right side actually, is going to be negative infinity as well. So the limit as x approaches a from the positive side of f of x is equal to negative infinity. So make sure you know how to properly denote those different types of behaviors, because that's key, and to make sure you don't get confused. Okay, now let's practice finding vertical asymptotes. Okay, so let's go through this theorem to make sure we go about this stuff properly. So if we have two functions f and g and they're continuous on some open interval containing c, and we know that both f of c and g of c are not both going to be 0, and we say that there's an open interval so that g of x is not 0 for all the values in that interval, then we can say that of another function that's equal to f of x over g of x will have a vertical asymptote at x equals c. Now, what does that mean? It's actually not that hard. It's just saying that the graph is going to get very, very large, very, very small from one side to another, because one of the values is getting or the denominator value is going to get very, very close to 0. Anyway, let's do some practice problems. This always makes it easier to understand. So we're just going to figure out the vertical asymptotes. we're not at this point required to actually understand and know precisely what the graph will look like. I'm still going to draw graphs of each function, but you're not expected to actually be able to figure these graphs out just like that. So first one, we have f of x is equal to 1 over 2 times x plus 1. So we basically are going to look for when is the denominator going to be equal to 0. Kind of just like when you were trying to figure out domains in pre-calculus, we find values where the function wouldn't be defined. So we set 2 times x plus 1 equal to 0, and that's just essentially setting x plus 1 equals 0, and so that'll be when x equals -1. So this function is not defined for x equals -1, so it's going to have an asymptote there because you can manipulate or change the form of it. So that's kind of what that theorem is saying. Now, again, you don't have to know how to draw this graph exactly, but I like to always have a picture so to better explain this and get a clear understanding of what's going on with these guys. So I have an asymptote, x equals -1, so something like that we could say. Now, again, it's not telling you to find, what the behavior is from the left and from the right, but you could always plug in values less than -1 to see what's going on the left side, and greater than -1 to see what's going on to the right side. And so you're going to actually then find that the function does something like this. It's actually going to go through the point 0, 1/2. And on the right side, it's going that way. So the limit from the left side as x approaches -1 will be -infinity, and the limit from the one-sided limit from the positive side would be positive infinity in this case. Now let's look at this next one, x squared plus 1 over x squared minus 1. So again, we can't factor anything else. X squared plus 1 is not factorable. So we set the denominator x squared minus 1 equal to 0 and solve for this. And you're going to find that it's going to be x squared is equal to 1, and you'll have two values. You'll have x equals 1 and then x equals -1 as well. So this graph has two values, or two asymptotes. So again, you're not expected to know what this graph will look like, but I'm going to draw a sketch so you can better understand what's going on. So -1, say that's x equals -1. We'll say that that's x equals +1. So what's going on with this graph? So if you want to figure out, what you could do is just plug in a value of x in here. Plug in, let's say like x equals negative, like 100 or something. So if we plug in, let me put it down here. If we plug in x equals -100, you would get that the value for y would be, let me calculate this, actually didn't do it, so 100 squared plus 1 divided by we actually get like a value almost like close to 1, something like right slightly above 1. So about 1 point, we'll say about 1. Okay, well that's weird. Okay, now that doesn't really actually help. So maybe there's a horizontal asymptote, but let's see what's going on when you're very, very close to, you know, -1 on the left side. So what if we put in like x equals -1.0001? What would we get for y? Now, if you did that, you would get, you know, let's see. I got a number, you know, like about 10,000. I got about 10,000.5, we could say. So since both these values are positive to the left of x equals -1, we can say, you know, confidently that the graph is going to, you know, do something like this. It's going to, you know, be going towards infinity on this side. Okay, so we can do that, you know, for the left side, and same thing for the right side. You can plug in like 1.001 and then like 1 million or something like that, and you would get, you know, again, you plug in like, it doesn't actually matter if you plug in, you know, negative or positive value in here, because when you square them, become positive, so you actually get the same numbers. So you're going to find that it's going to be symmetrical along these. So the graph is going to actually approach infinity from the right side limit of this asymptote and from the left side limit of that asymptote. Let me draw this a little better. Now, what about the middle? Well, again, you could just plug in some values. If we plug in, you know, x equals 0 into here, we would get 1 over -1. So we get y equals -1. And if you plug in the value between -1 and 0, you would actually get a very small negative number. If you plugged in like -0.999999, you would get a number like, you know, going towards, you know, negative infinity, like be like -10,000 or something like that. And same thing over here. If you plugged in 0.999999, you would get values that are negative. So the graph actually does something like this. Now, again, you're not told yet, and you're not expected to find exactly what this graph will look like. That's not what we're learning here in this part of calculus. But I suppose I always like to build some, you know, foundational skills, because you don't want to go mindlessly about this, especially when you're graphing. Always keep in mind what you're doing when you're graphing. Okay, so let's look at a couple more now. Let's look at this. Let's look at the trig function, f of x equals the cotangent of x. And this, let's remember, you know, what cotangent of x even is. So f of x equals the cotangent of x. We know the cotangent of x is just the same as, you know, the reciprocal of the tangent of x, or the which is equal to the cosine of x divided by the sine of x. So it's not going to be defined for when sine of x equals 0, because that'll make the denominator 0. So when the sine of x equals 0, if you remember, your unit circle very well, will be at 0. Let me actually write. Be at x equals 0, positive and negative pi, positive and negative 2 pi, positive and negative 3 pi, and so forth. So every pi unit, since it's, you know, periodic. So we just have asymptotes at these points, and you've probably already, you know, seen this graphs and know that because in pre-calculus. So your asymptotes are, you know, Let's just draw a little sketch to get a kind of basic idea of what's going on here. So you're having asymptote, through the y-axis, x equals 0. You're going to have 1 at, x equals pi, x equals 2 pi, x equals negative pi, and so forth. And that makes sense because these are the functions look like, because if you recall what the cotangent function looks like, it's going to do like kind of the backwards version of the tangent. It's going to have this curvy thing like that. So these are basically the equations of your asymptotes. All right, now here for D, here's an example of when you can actually do something with a function to change it. So you can factor out the numerator into x plus 4 times x minus 2. And the numerator or denominator you can factor into x minus 2 times x plus 2. So you can actually cancel out those factors. And then you end up with another, function. We'll call it g of x, which is equal to x plus 4 over x plus 2. So if you remember, like what we did a lesson or two ago, this function is going to be identical to this one. The g of x is identical to the graph of f of x, except for the value at x equals 2 or x equals negative 2 and 2. Because at those points, it's undefined, remember. So let's write that out. Now, if we were to graph this, we would have asymptotes at these points, but not at both of them. So let's actually graph this. So let me show you what's going on. You would have an asymptote at the x value that you could not remove. We were able to remove the x plus 2 at x equals 2. So at x equals 2, we actually are going to have a hole. And you're going to have an asymptote at x equals negative 2. Because we weren't able to remove that. So what this graph is actually going to look like, if you're going to actually to plug in values, is you're going to have the graph, approaching the asymptote negative 2 from the left side, going downwards like that. And then from the right side, it would be like this, doing something like this. Now this is I'm saying that this is for f, this is our original function graph. But remember, since f is not defined for x equals 2 and negative 2, we took care of negative 2, but at 2, we're going to have to put a hole at. So at 2, if we evaluated it, you would get 6 over 4, so 1.5. So we would have a hole. So let's write this formally. So f of x has asymptote x equals negative 2. has asymptote s equals -2, and it has a hole at 2, 1.5. Okay, so let's summarize some kind of general strategies when we're working with these types of functions and figuring out what the vertical asymptotes are. So if you can factor and reduce, like we did in this case, if the limit is undefined, so in this case it was undefined, x equals -2, then there's a vertical asymptote there. But if the limit exists, so in this case it would exist at 2, then there's going to be a hole in the graph. So if you remember that, it's going to make your life a lot easier when you're figuring out vertical asymptotes.